electromagnetic. This is in fact a very wide-ranging spectrum, which goes from the low-energy radio waves through microwaves into the infrared. Then you have the very narrow band of the visible spectrum, and then out into the ultraviolet and on into X-rays and gamma rays. So while we are all familiar with rainbows and the visible spectrum of light, we can actually use almost any part of the whole electromagnetic spectrum for analytical purposes. But to understand why it's possible, we have to start looking at the structure of the atom. So at the end of the 19th century, there was a model of the atom which is described as the plum pudding model. And in this model, the atom was a large, positively charged object with negatively charged electrons embedded in it, rather like the raisins in a Christmas pudding. This model was dropped based on experimental work, and Rutherford proposed a new model. In his new model, the atom consisted of a small, very dense, positively charged core called the nucleus, which was later found to be made up of protons and neutrons. And almost all the mass of the atom is concentrated in that nucleus. The electrons, which are negatively charged, orbit around that nucleus. So most of the atom is free space, and the electrons are moving through that free space as they orbit the nucleus. Now there's a problem with this model which needs to be explained. If you have this small, dense, positively charged nucleus in the center, surrounded by these negatively charged electrons, then the atom should destroy itself, because the positive nucleus should attract the negative electrons, and the electrons should just collapse into the nucleus, and that's the end of your atom. But atoms don't destroy themselves, they are stable. So a new theory was needed, and this was